The question hangs in the cosmic silence, a query whispered by humanity for as long as we have looked up at the pinpricks of light in the velvet darkness. It is perhaps the most profound question we can ask: are we alone for millennia? This was a question for philosophers and poets, a thought experiment confined to the realms of faith and imagination. But today, it has become a question for scientists, engineers, and astrobiologists. We have moved from asking if we should search to actively debating the best methods how. The journey from ancient wonder to scientific inquiry has been long and fraught with dead ends. But it has brought us to a remarkable threshold. We are, without exaggeration, the first generation of humans with the technological capacity to find a definitive answer. To understand how close we are, we must first appreciate the scale of our ignorance and the path we took to chart it. Our cosmic loneliness was once a given, an axiom of a universe designed with Earth at its sacred center. To suggest otherwise was heresy. Giordano Bruno, a 16th century Dominican friar, was burned at the stake for his visions of an infinite universe containing countless other worlds, many of which, he reasoned, must be inhabited. His was a philosophical leap, an intuition born from the sheer grandeur of the cosmos. It would take a technological one to begin to ground such ideas in observation. That leap came with Galileo Galilei and his telescope, when he pointed his crude instrument at Jupiter and saw 4 tiny moons orbiting the gas giant. He did more than discover new celestial bodies, he shattered the geocentric model of the universe. If another planet had its own moons, then Earth was not unique. It was just another world, following the same physical laws as everything else. This was the conceptual dawn of astrobiology. If the laws are the same everywhere, and the ingredients are the same everywhere, why should the outcome, life itself, be unique to here? This new perspective fired the imagination. In the late 19th century, Percival Lowell, a wealthy Boston astronomer, became fixated on Mars. Through his powerful telescope in Arizona, he meticulously mapped what he believed were vast, linear canals crisscrossing the planet's surface. To him, these were not natural formations. They were feats of planetary engineering, irrigation channels built by an advanced, dying Martian civilization to ferry water from the polar ice caps to their arid equatorial cities. It was a stunning, romantic vision that captivated the public, fueling decades of science fiction. Of course, we now know these canals were an illusion, a combination of low-resolution optics and the human brain's powerful tendency to see patterns in random noise. The Martian canals were not on Mars, they were in Lowell's eye. This episode served as a crucial lesson. The desire to find life is so strong it can lead us to invent it. The modern search began not with sight, but with sound. By the mid-20th century, we had mastered a new sense, radio. We understood that radio waves travel at the speed of light and can pass through the dust and gas that obscure visible light. A young radio astronomer named Frank Drake reasoned that if another civilization had developed technology, they might also have discovered radio and would be using it to communicate, perhaps even deliberately broadcasting a signal for others to find. In 1960, Drake conducted Project Ozma, the first formal search for extraterrestrial intelligence, or SETI. For a few months, he aimed the 85-foot radio telescope at Green Bank, West Virginia, toward to nearby sun-like stars, Tau Ceti and Epsilon Eridani. He tuned his receiver to a frequency of 1420 MHz, the natural emission frequency of hydrogen gas, the most common element in the universe. Drake reasoned any savvy celestial communicators would choose this cosmic water cooler as a logical, universal channel to broadcast on. He found nothing but static, but the silence was not a failure. It was a first data point. The search had begun. To organize the monumental task ahead, Drake formulated what is now known as the Drake equation. It is less an equation meant to be solved for a precise number, and more a framework for organizing our ignorance. It breaks down the grand question how many communicative civilizations are in our galaxy into a series of smaller, more manageable problems. The rate of star formation, the fraction of those stars with planets, the number of those planets that are suitable for life, the fraction on which life actually appears, the fraction of that life which becomes intelligent, the fraction of intelligent life that develops detectable technology, and finally, the length of time such a civilization broadcasts its presence. When Drake first wrote it, nearly every term was a wild guess. But in the decades since, we have begun to fill in the blanks with actual data. The first two terms, the rate of star formation and the fraction with planets, have been spectacularly resolved. Thanks to missions like NASA's Kepler Space Telescope, we now know that planets are not the exception, they are the rule. The data suggests there are more planets than stars in the Milky Way. Our galaxy is teeming with worlds. We have moved from a universe of suspected planets to a universe of confirmed trillions. The next term, the number of planets in the habitable zone, is where the modern search is focused. This is the so-called Goldilocks zone, the orbital band around a star where temperatures are just right for liquid water to exist on a planet's surface. Not too hot, not too cold. Kepler and its successor, TESS, have identified thousands of candidate worlds in these zones. We have found rocky, Earth-sized planets orbiting in the habitable zones of their stars. Proxima Centauri b, a planet orbiting our very nearest stellar neighbor, is one such world. TRAPPIST-1, a star system just 40 light-years away, holds a staggering 7 rocky planets, at least 3 of which are in its habitable zone. These are no longer abstract concepts. They are destinations. We have maps. But finding a planet in the right place is just the beginning. The real challenge is the next term in the equation, the fraction on which life actually arises. How do we bridge the gap between a promising rock and a living world? This is where the James Webb Space Telescope enters the story. JWST is a revolutionary instrument. By analyzing the starlight that passes through an exoplanet's atmosphere, it can detect the chemical composition of its air. It is searching for biosignatures, chemical fingerprints that are difficult to explain without the presence of biological processes. What are these fingerprints? We look for the familiar: water vapor, carbon dioxide, methane. But the true holy grail would be finding gases that are out of chemical equilibrium, like finding abundant oxygen and methane in the same atmosphere. On Earth, oxygen is a reactive gas constantly replenished by photosynthesis. Methane is produced by microbial life. Left to their own devices, these two gases would quickly react and destroy each other. Finding them together in large quantities strongly suggests a constant, planet-wide biological source. JWST is capable of making such a detection. For the first time, we are not just looking for worlds. We are sniffing their air for the breath of life. Yet, this entire approach is built on an assumption that extraterrestrial life will be like us. It assumes carbon-based life that depends on liquid water. But what if life can take on vastly different forms? The universe is more creative than we can imagine. On our own planet, we find extremophiles, organisms that thrive in conditions we once thought unsurvivable. In boiling volcanic vents on the ocean floor, in the crushing pressure of the deep sea, in hyperacidic rivers, and frozen solid within Antarctic ice, these tenacious creatures prove that the definition of habitable is far broader than a comfortable, sunlit Earth-like surface. This realization has expanded our search to our own cosmic backyard. We once thought Mars was a dead, rusted globe. Now rovers like Perseverance are drilling into an ancient river delta, searching not for current life, but for the fossilized chemical remains of microbial life that may have existed billions of years ago when Mars was a warmer, wetter world. Finding even a single, indisputable microfossil on Mars would be one of the most significant discoveries in human history. It would prove that life is not a fluke unique to Earth. It would mean that the universe, at least on a microbial level, is likely filled with life. Even more tantalizing are the ocean moons of Jupiter and Saturn. Jupiter's moon Europa and Saturn's moon Enceladus are both covered in a thick shell of ice, but beneath it, scientists are almost certain there are vast, globe-spanning oceans of liquid salt water. These oceans are not warmed by the sun, but by the constant gravitational squeezing and stretching from their parent planets, a process called tidal heating, on the floors of these dark, alien oceans. There could be hydrothermal vents, just like those on Earth where life is thought to have possibly originated. Enceladus even offers us a shortcut. It has been observed actively spewing massive plumes of water vapor from its south pole into space. A future probe could fly through these plumes and sample the contents of its subsurface ocean without ever having to land and drill through miles of ice. We could taste an alien sea. And then there is Titan, Saturn's largest moon. Titan is a truly bizarre world. It has a thick, nitrogen-rich atmosphere, thicker than Earth's, and weather systems with clouds, rain, rivers, and lakes. But on Titan, the liquid is not water. It is methane and ethane. Could a completely different form of life, one not based on water, exist in its frigid hydrocarbon seas? If we were to find life there, it would rewrite the textbooks on biology. This brings us back to the Great Silence. We have built bigger and better radio ears. We have scanned the skies for decades. We have found thousands of planets, and yet the universe remains stubbornly quiet. This is the heart of the Fermi paradox. Given the age and size of the universe and the sheer number of potential worlds, someone should have said hello by now. Where is everybody? The paradox gives rise to a sobering concept, the Great Filter. The idea is that there is some barrier, some evolutionary or technological hurdle, that is exceedingly difficult for life to overcome. The question is, where is that filter in our timeline? Is it behind us? Perhaps the initial leap from non-life to life, or the jump from simple prokaryotic cells to complex eukaryotic cells, is an event so statistically improbable that it has only happened once, here on Earth. If so, we may be the first and only intelligent beings in our galaxy. We won the cosmic lottery. Or, more ominously, is the Great Filter ahead of us? Perhaps intelligence and technology are common, but they inevitably lead to self-destructs. Civilizations might wipe themselves out through nuclear war, uncontrolled artificial intelligence, resource depletion, or climate catastrophe. In this scenario, the silent sky is not empty. It is a graveyard. It is a warning. The silence is the sound of countless civilizations that reached our level of technological prowess and failed to survive it. Of course, there are other, less terrifying possibilities. Perhaps the distances are simply too vast and the energy requirements for interstellar communication or travel are too great for any practical civilization to overcome. Or maybe they are communicating, but in ways we cannot yet comprehend, using technologies like manipulated neutrinos or gravitational waves that are far beyond our current grasp. It would be like trying to find a fiber optic data stream with a 19th century telegraph. There is also the zoo hypothesis that advanced civilizations are out there, but they are deliberately hiding from us, observing us from a distance, as one might observe animals in a protected nature preserve, waiting for us to reach a certain level of maturity before making contact. So, how close are we? We are standing on a precipice of discovery. We have moved beyond philosophical speculation and have built a rigorous, data-driven science of astrobiology. We have identified specific, promising targets, both in nearby star systems and within our own. We have deployed the tools like JWST that can, for the first time, analyze the atmospheres of these worlds for the telltale signs of life. The discovery of microbial life, whether as a fossil on Mars or a chemical signature in an exoplanet's atmosphere, feels tantalizingly close. Many scientists believe it is a question of when, not if, and that it could happen within the next decade or two. It would fundamentally change our perspective, confirming that we are part of a larger biological universe. The discovery of intelligent life is a far more profound and uncertain question. The silence is real, and the implications of the Fermi paradox are sobering. But our search has only just begun. We have been listening for a mere cosmic second on a single, narrow band. The universe is ancient, and we are infants shouting into the void. Ultimately, the search for extraterrestrial life is as much a search for ourselves. It forces us to look inward, to consider the fragility of our own civilization and our place in the grand cosmic scheme. To find life elsewhere would be to find a mirror, reflecting a universe far richer and more complex than we ever dreamed. To find only silence would be to understand the profound preciousness of the life that exists here on this pale blue dot. The journey to answer the question, regardless of the outcome, is what will define this century of exploration. We are listening, we are looking, and for the first time in the 4 billion-year history of life on Earth, we are ready for an answer.